Part 1. The Science of Making Better Decisions. Introduction. What is operations research? Imagine you are the captain of the Indian cricket team. You have 11 players, but you need to decide the batting order. Who goes first? Who bowls the last over? Or, imagine you are a manager at Swiggy. You have 1,000 orders and 50 delivery drivers. Who delivers what? Operations research, OR, is the mathematical way of answering these questions. It is the science of better. It uses math, logic, and data to find the optimal solution, the absolute best possible answer when you have limits, like limited money, limited time, or limited people. If you act on gut feeling, you might get it right 50% of the time. If you use OR, you aim to get it right 100% of the time. The secret formula: how to think in OR. Almost every OR problem has 3 parts. We will use this structure for every example below. 1. Decision variables. What are the things you can control? Example: how many samosas to make? 2. Objective function. What is your goal? Example: maximize profit or minimize time. 3. Constraints. What is stopping you? Example: limited potatoes, limited oil, only 24 hours in a day. 30 real-life operations research examples in India. 115. Here are the first 15 examples. We will look at the problem, the specific OR concept used, and exactly how to write the math for it. 1. The thali problem, diet problem. Concept: linear programming, LP. The scenario: you are a student in a hostel in Kota. You want to eat a healthy dinner. You have 2 options at the mess, dal and roti. You need at least 50 grams of protein and 200 grams of carbs to stay energetic. One bowl of dal has 10 grams protein, 20 grams carbs, and costs 40. One roti has 2 grams protein, 25 grams carbs, and costs 10. Goal: spend the least amount of money while meeting your nutrition needs. How to form the equation: let $x equals number of dal bowls. Let $y equals number of rotis. 1. Objective: minimize cost. $E equals 40x plus 10y. 2. Constraints: the rules. Protein rule: $10x plus 2y 50. You need at least 50 grams. Carb rule: $20x plus 25y 200. You need at least 200 grams. Logic rule: $x 0, y 0. You can't eat negative food. The solution: you draw these lines on a graph. The feasible region is the area where you satisfy all rules. You check the corners of that region. You might find the answer is something like 3 bowls of dal and 5 rotis. Real business use: ideally, hospitals in India use this to plan patient meals, and poultry farms use this to mix chicken feed, corn versus soy, to minimize cost while maximizing bird growth. 2. The Kirana store stock. Inventory control. Concept: economic order quantity, EOQ. The scenario: your uncle runs a Kirana shop in Mumbai. He sells basmati rice. If he orders too much at once, he has to pay rent to store it, and rats might eat it, holding cost. If he orders too little, he has to keep paying for the delivery truck again and again, ordering cost. Goal: find the magic number to order so the total cost is lowest. The math: EOQ formula. $EOQ equals SQRT frac 2 CDOTD CDOT SH $D equals demand. Example: he sells 1,000 kilograms or year. $S equals setup or ordering cost. Example: 500 per truck delivery. H equals holding cost. Example: 2 per kilogram per year to store. The solution: $EOQ equals SQRT frac 2 CDOT 1000 CDOT 502 equals SQRT 500,000 approx 707 text kilogram $. So he should order 707 kilograms at a time. Not more, not less. Real business use: Flipkart and Amazon use this logic for millions of items in their warehouses to balance storage costs versus delivery costs. 3. The Bengaluru traffic signal queuing theory. Concept: M or 1Q. The scenario: you are stuck at the Silkboard junction in Bengaluru. Cars arrive randomly, and the traffic light lets them pass at a certain speed. Goal: the traffic police want to adjust the green light duration so the average waiting time is less than 2 minutes. How to form the equation? We use lambda, and mu, lambda equals arrival rate. Example: 10 cars per minute arrive. Mu equals service rate. Example: the light lets 12 cars per minute pass. The formula: average wait time, W equals frac 1 mu lambda W equals frac 11210 equals frac 12 text minute 30 seconds If arrivals lambda increase to 11. 9 cars per minute, the wait time shoots up to 10 minutes. This explains why a tiny increase in traffic causes massive jams. Real business use: call centers, Airtel or Jio. Use this to decide how many agents to have on shift so you don't wait on hold for too long. 4. The Big Fat Indian Wedding knapsack problem. Concept: integer programming or knapsack. The scenario: you are planning your sister's wedding. You have a budget of 5 lakhs for extra luxuries. You have a list of options, but you can't afford all of them. 1. DJ night. Cost: 2L. Fun value: 90. 2. Drone photography. Cost: 1L. Fun value: 60. 3. Exotic dessert counter. Cost: 3L. Fun value: 80. 4. Firecrackers. Cost: 1L. Fun value: 40. Goal: maximize fun value without exceeding 5L. How to form the equation? Let $x1, x2, x3, x4 be binary, 1 if you choose it, 0 if you don't. Maximize Z, fun, $90x1 plus 60x2 plus 80x3 plus 40x4. Constraint: budget, $2, x1 plus 1 by 2 plus 3 by 3 plus 1 by 4 la $5. The solution: you can't just pick the highest fun DJ and stop. Option A, DJ plus dessert equals 5L. Total fun equals 90 plus 80 equals 170. Option B, DJ plus drone plus firecrackers equals 4L. Total fun equals 90 plus 60 plus 40 equals 190. Winner: option B gives more fun for less money. Real business use: investment bankers use this to pick which stocks to buy. Logistics companies use this to decide which boxes to fit into a truck. 5. The school bus route traveling salesman problem. Concept: network optimization. The scenario: a school bus driver needs to pick up 10 students from different colonies in Delhi, Rohini, Pitampura, Dwarka, etc., and reach the school. Goal: visit every student's house exactly once and return to the depot using the least amount of diesel, shortest distance. The logic: this is harder than it looks. With just 10 houses, there are $3,628, $800 possible routes. OR algorithms, heuristics. Look for the next nearest neighbor. 1. Start at school. 2. Go to the closest student, student A. 3. From A, go to the closest unvisited student, student B. 4. And so on. Real business use: Zomato and Swiggy use this every second. When a delivery partner has 3 orders to deliver, the app calculates the shortest path to drop them off to save fuel and time. 6. Board exam preparation, PERT, or CPM. Concept: project management, critical path method. The scenario: you have 15 days before your math board exam. You have 5 chapters to study. Some chapters depend on others. You can't do calculus before algebra. Task A, algebra, 3 days. Task B, trigonometry, 2 days. Task C, calculus, requires A and B, 5 days. Task D, statistics, independent, 4 days. Goal: finish fastest. The diagram: path 1, A, C, equals 3, plus 5, equals 8 days. Path 2, B, C equals 2 plus 5 equals 7 days. Path 3, D equals 4 days. The critical path. The longest path determines how soon you can finish. Here, it is path 1, 8 days. If you delay algebra, task A, by even 1 day, your whole study plan is delayed. But if you delay statistics, task D, by 2 days, it doesn't matter because it's not on the critical path. Real business use, construction companies, like L&T, use this to build metros. They know that laying tracks cannot happen before digging tunnels. 7. Buying vegetables, the news vendor problem. Concept: stochastic inventory. The scenario: a vegetable vendor sits in the local mandi. He buys tomatoes for 20 per kilogram and sells them for 40 per kilogram. If he buys too many, they rot by evening, loss of 20 per kilogram. If he buys too few, customers go away, loss of potential profit 20 per kilogram. Goal: how many kilogram to buy if demand is uncertain. The logic: OR uses probability. If there is a 50% chance of selling 50 kilograms and a 20% chance of selling 80 kilograms, the algorithm calculates the expected value. He should stock slightly more than average because the profit of selling 120 is equal to the cost of wasting 120. If profit was higher, 50, and cost of waste was low, 5, he would stock much more. Real business use: newspaper stands, hence the name, and bakeries use this. They bake more cakes than they expect to sell because running out is worse for their reputation than throwing one cake away. 8. Auto rickshaw surge pricing. Dynamic pricing. Concept: revenue management. The scenario: it is raining in Mumbai, everyone wants an auto. Normal price, 50. Demand, 100 people. Supply, 20 autos. Goal: balance supply and demand. The math: the price, dollars P dollars, is a function of demand, dollars D dollars, and supply, dollars S dollars. Dollars P equals text, base price, times left, frac, DES right, times K, dollars. If demand is 5x the supply, the algorithm increases the price. Why? $and D1. To discourage people who don't really need the ride, reducing D2. To encourage auto drivers to come out into the rain to earn more, increasing S real business use, Ola, Uber and airlines, Indigo or Air India. This is why flight tickets are expensive during Diwali and cheap in July. 9. Assigning fielders in cricket, assignment problem. Concept: Hungarian method. The scenario: you are the captain, Rohit. You have 4 fielders: Virat, Jadeja, Bumrah and Shami. You have 4 positions: slips, long on, point and fine leg. You have a score for how good each player is at each position, 1 to 10. Jadeja, 10 at point, 9 at long on. Bumrah, 4 at point, 8 at fine leg. Goal: assign each player to exactly 1 position to maximize the total team fielding score. How to form the equation: let $xij equals $1 if player $I is at position $j. Maximize sum: text skill score times xij . Subject to: each player has 1 spot, each spot has 1 player. Real business use: IT companies, Infosys or TCS, use this to assign developers to projects. If developer A is good at Java and developer B is good at Python, you don't swap them. 10. Manufacturing idly batter, product mix. Concept: linear programming. The scenario: ID Fresh Food has a factory. They have 1,000 kilograms of rice and 500 kilograms of urad dal. Idli batter requires 3 parts rice, 1 part dal. Profit 20 or PKT. Dosa batter requires 2 parts rice, 1 part dal. Profit 15 or PKT. Goal: how many packets of idli versus dosa batter to make to get maximum profit. The equation: maximize $z equals 20, text idli, plus 15, text dosa, dollars. Subject to: rice used $li $1,000. Dal used $li $500. Real business use: oil refineries, Reliance Jamnagar. They decide how much crude oil to turn into petrol, diesel, or jet fuel based on market prices and chemical constraints. 11. Choosing a mobile plan. Game theory. Concept: zero-sum game or Nash equilibrium. The scenario: Jio launches a new plan, Plan A. Airtel sees this. Airtel has two choices: match the price, choice 1, or offer more data, choice 2. If Airtel lowers price, Jio might lower it further, price war. Both lose money. If Airtel offers data, they keep their price high. The logic: game theory helps you analyze what your opponent will do. You assume your opponent is smart. The Nash equilibrium is a situation where neither company wants to change their strategy because they are doing the best they can given what the other is doing. Often, the result is both companies offer very similar plans, $299 for one, 5 gigabytes a day. Real business use. Coca-Cola versus Pepsi strategies. Flipkart, Big Billion Days versus Amazon Great Indian Festival. 12. Investing pocket money, portfolio optimization. Concept: Markowitz model, mean variance analysis. The scenario: you have 10,000 saved. You can put it in 1. Bank FD, low risk, low return, 6%. 2. Stock market, high risk, high return, 15% or minus 10%. Goal: get the best return for a risk level you can handle. The logic: OR says don't put all eggs in one basket. We define variables for the percentage of money in FD, $W $1, and stocks, $W $2. We minimize the variance, risk, subject to a target expected return. The math tells you the perfect split, say 70% in FD and 30% in stocks, to ensure you don't lose all your money. Real business use. Mutual funds, HDFC Mutual Fund, SBI Mutual Fund, run these models on supercomputers every day to manage crores of rupees. 13. Water tanker supply in summer, transportation problem. Concept: transportation simplex method. The scenario: Chennai is facing a water shortage. Sources: 3 lakes, A, B, C with water. Destinations: 4 neighborhoods: T Nagar, Ajar, Velatri, Ananagar, needing water. Cost: the cost to drive a tanker from Lake A to T Nagar is different from Lake A to Adyar. Goal: distribute the water to meet everyone's needs at the minimum transport cost. The table: you create a matrix of costs. From or to T Nagar Adyar supply. Lake A 50,80,100 L. Lake B 60,40,200 L. Demand 150 L 150 L. The solution: you don't just send the closest water. Sometimes sending water from a slightly further lake is better if it frees up the nearby lake for a desperate neighborhood. Real business use. FCI, Food Corporation of India, moving wheat and rice from Punjab to Kerala. 14. Metro train maintenance. Replacement theory. Concept: replacement policy. The scenario: Delhi Metro uses thousands of light bulbs and wheels. Strategy A: wait for a bulb to fuse, then replace it. High labor cost to send a guy for just one bulb. Strategy B: replace all bulbs every 6 months, even if they are working. High material cost, low labor cost. Goal: minimizing the sum of material cost plus labor cost. The logic: as time passes, the probability of failure increases. OR calculates the average life and finds the sweet spot. It is often cheaper to replace everything at once, group replacement, than fixing things one by one. Real business use: factory machines, aircraft engine maintenance, and even changing tires on a fleet of trucks. 15. Hospital bed allocation, resource allocation. Concept: integer programming. The scenario: during a dengue outbreak, a hospital has 50 beds. Patients come in with different severities: critical, needs ICU; moderate, needs ward; mild, sent home. Resources needed: doctors, oxygen, beds. Goal: save maximum lives. The constraints: you cannot give one. 5 beds, must be integer. Total oxygen usage: $lay, tank capacity. Doctor, hours, $lay, shift timings. The solution: the model prioritizes patients. It might say, admit 10 critical patients to ICU and 40 moderate to ward. Send mild cases home with medicine. This removes human bias and panic from the decision. Real business use. Government policy during pandemics. COVID-19 vaccine distribution strategies were based on this. Pause for reflection. We have covered the first 15 examples, moving from simple diet plans to complex hospital management. You can see that operations research isn't just boring math equations. It is the logic behind how the world runs efficiently. In Part 2, we will cover examples 1630, including how Netflix recommends movies, Markov chains, how much cash an ATM should hold, how to win at waiting in lines at Tirupati, why airlines overbook flights. Would you like me to proceed with Part 2 and the remaining 15 examples now? Here is Part 2 of the Comprehensive Operations Research OR Notes. This covers examples 16 through 30, focusing on slightly more advanced but highly practical concepts used every day in India. Part 2, Advanced Decision-Making and Strategy. 30 real-life operations research examples in India, 1630. 16. YouTube and Hotstar recommendations, Markov chains. Concept, Markov chains, stochastic processes. The scenario, you just watched a cricket highlight on Hotstar. What should the app show you next? There is a probability you will watch another highlight, 70%. There is a probability you will watch a movie, 20%. There is a probability you will close the app, 10%. The logic, a Markov chain predicts the next state based only on the current state. It doesn't care about what you watched 5 years ago, only what you are watching right now. The math, transition matrix. We create a grid of probabilities, $P equals, begin B matrix, 0. 7 and 0. 2 and 0. 1, 0. 1 and 0. 8 and 0. 1. And B matrix, dollars. If millions of users follow this pattern, Hotstar knows exactly which servers to prepare for high traffic. Real business use, Google PageRank uses this to decide which websites are important. Keyboard apps, Gboard, use this to predict the next word you will type. 17. The ATM cash problem. Inventory management. Concept, stochastic inventory control. The scenario, you are the manager of an SBI ATM in a busy market. Too much cash. It sits idle, dead money, and is a security risk. Too little cash. The ATM runs dry. Customers get angry, and they switch to HDFC. Goal, how much cash to load every morning. The logic, you look at past data. Weekdays, withdrawal average is 2 lakhs. Weekends, withdrawal average is 5 lakhs. Diwali or salary day, first of month. Withdrawal average is 10 lakhs. The solution, you set a safety stock level. If the average is 2L, you might load 2. 5L to cover unexpected spikes. Standard deviation. You balance the cost of idle cash versus cost of losing a customer. Real business use, banks, SBI, ICICI, use this for thousands of ATMs. They also use it to decide when to send the cash van, refilling schedule. 18. Tirupati Darshan, queuing theory, multiple servers. Concept M or C queue, multiple servers. The scenario, Tirupati Balaji Temple is one of the most visited places in the world. 50,000 plus pilgrims visit daily. If there is only one entry gate, the line will stretch to Chennai. They open multiple servers, ticket counters, or entry gates. The logic? Arrival rate, lambda dollars. 100 pilgrims per minute. Service rate per gate, mu dollars. 10 pilgrims per minute. Number of gates, C dollars. To keep the line moving, the total capacity, $C times mu dollars, must be greater than arrival, lambda dollars. $C times 10 greater than $100. So they need at least 11 gates just to keep up. To reduce the queue, they might open 15 gates. Real business use, toll plazas, FASTag. If the line gets too long, they open an extra lane. Supermarkets, Big Bazaar, deciding how many billing counters to open on Sunday evening. 19. Airline overbooking, yield management. Concept, probabilistic overbooking. The scenario, an Indigo flight from Delhi to Mumbai has 180 seats. Indigo sells 190 tickets. Why? They know from historical data that approx 5% of people will miss the flight or cancel last-minute no-shows. The risk: if 190 people show up, 10 are angry. Indigo has to pay them compensation, cost of overbooking. If only 170 show up, the flight flies with 10 empty seats. Cost of spoilage. The math: they calculate the expected cost of bumping a passenger versus the revenue of selling that extra seat. $P, N greater than 180 times text cost of bump, text ticket price, $. As long as the ticket price is high enough to cover the rare risk of paying compensation, they will overbook. Real business use: hotels, Taj, Oyo, also do this. They book more rooms than they have, expecting cancellations. 20. Building a flyover, crashing project time. Concept: time-cost trade-off, CPM crashing. The scenario: a contractor has 12 months to build a flyover. The government offers a bonus of 1 crore if he finishes in 10 months. Normal cost: 50 crores. To finish faster, he needs to hire double labor and work at night, overtime. Crash cost: extra cost, 50 lakhs per month saved. The calculation: save 2 months equals cost increases by 1 crore, $50L times $2. Bonus received equals 1 crore. Net gain equals 0. However, finishing early frees up his machines for a new project. So it is worth it. Real business use: road construction, NHAI, and software development. Managers constantly decide if they should add more programmers to launch the app sooner. 21. Amazon warehouse locations, center of gravity. Concept: facility location problem. The scenario: Amazon wants to build a main warehouse to serve Pune, Mumbai, and Nashik. Where should they put it? Mumbai: demand 10,000 packages per day. Quartz, 1972. Pune: demand 8,000 packages per day. Quartz, 1873. Nashik: demand 2,000 packages per day. Quartz, 2073. The math: weighted average. You don't put it in the middle. You put it closer to where the most demand is, Mumbai. $X equals frac 10,019 plus 8,018 plus 2,020, 10,000 plus 8,000 plus $2,000. This gives the exact GPS coordinate that minimizes total truck driving distance. Real business use: Domino's Pizza deciding where to open a new kitchen to ensure 30-minute delivery. Fire stations positioned to reach the most houses in minimum time. 22. Making paint colors, blending problem. Concept: linear programming, minimization. The scenario: Asian Paints needs to make royal blue. Ingredient A: blue pigment. Costs 500 per liter. Ingredient B: filler or base. Costs 50 per liter. Ingredient C: shine additive. Costs 200 per liter. Constraints: 1. Must have at least 40% pigment for color depth. 2. Must have at least 10% shine. 3. Total quantity equals 1,000 liters. Goal: minimize cost while meeting quality standards. The solution: the LP model finds the exact recipe, maybe 400 L pigment, 100 L shine, and 500 L base. Any other mix is either too expensive or low quality. Real business use: Amul milk, mixing buffalo milk, which is high fat, with cow milk to get standardized milk. Cement manufacturers. 23. Nurse rostering in hospitals, scheduling. Concept: integer programming or set covering. The scenario: Apollo Hospital has 100 nurses. Needs: 30 nurses in morning, 20 in afternoon, 15 at night. Rules: no nurse can work 2 shifts in a row. Every nurse needs 1 day off a week. Goal: minimize total staff needed while covering all shifts. The logic: this is a puzzle. If you assign nurse A to Monday night, she cannot work Tuesday morning. $. Minimize sum $X Subject to $sum AIJXJGE. Text requirements for shift I $. Real business use: call centers, police patrols, and airline crew scheduling. Pilots have strict rest rules. 24. Betting on cricket or stocks, decision trees. Concept: decision analysis. The scenario: you have 1 lakh. You can invest in a startup friend is launching. Choice A: invest Success, 30% chance. Return 5 lakhs. Failure, 70% chance. Return 0. Choice B. Keep in bank. Certainty, 100% chance. Return 1.06 lakhs. The math, expected monetary value. EMV. EMV. Invest equals dollars. 0. 30 times 5. 0, 0. 0, 0, 0. Plus 0. 70 times 0 equals 1. $50,000. EMV. Bank equals $1. 06. 000 Conclusion. Mathematically, investing is better. 1. 5L greater than 1. 06L. But if you are risk-averse, you can't afford to lose the initial 1L. You might choose the bank. OR helps calculate the risk. You make the choice. Real business use. Oil companies deciding whether to drill a well cost 100 CR with a 20% chance of finding oil. 25. The carpenter's problem. Cutting stock. Concept 1D cutting stock problem. The scenario. A carpenter has standard 10-foot plywood sheets. He needs to cut pieces for a wardrobe, 5 pieces of 3 feet, 2 pieces of 4 feet, 3 pieces of 5 feet. Goal. Use the minimum number of 10-foot sheets. Minimize waste. The logic, bad way. Cut 3 feet, 3 feet, 3 feet from one sheet. Leaves 1 foot waste. Smart way. Cut 4 feet, 4 feet, and 2 feet. Wait. Need 2. 5. Optimal pattern, mix and match. Example. 1 sheet equals 4 feet plus 3 feet plus 2. 5 feet, total 9. 5 feet, only 0. 5 feet waste. Real business use. Steel industry, cutting steel rods. Paper mills, cutting large rolls into A4 size. Textile industry, cutting shirt patterns from cloth rolls. 26. When to sell your car. Dynamic programming. Concept, replacement theory, dynamic programming. The scenario, you bought a bike for $80,000. Year 1, resale value $60K. Maintenance cost $2K. Year 2, resale value $50K. Maintenance cost $5K. Year 5, resale value $20K. Maintenance cost $15K. Goal, minimize the average annual cost over time. The logic, you calculate the cost per year for keeping it 1 year, 2 years, 3 years. Initially, the cost drops, depreciation slows down. Eventually, maintenance gets so high the cost rises again. The lowest point of the U-curve is the optimal time to sell. Real business use. Trucking companies deciding when to retire old trucks. Laptop replacement policies in IT companies. 27. IPL auction strategy, bidding strategy. Concept, game theory, auction theory. The scenario, Mumbai Indians wants to buy a specific player. They have a budget of 10 crossing. They know CSK also wants him, but suspect CSK only has 8 CR left. The strategy, if MI bids 10 CR immediately, they waste money. If they bid 2 crossing, CSK will raise it. Optimal strategy, bid just enough to make CSK drop out, shade the bid. If they know CSK's limit is 8 crossing, I should be prepared to bid 1 crossing, but start slow to test the waters. Real business use, government spectrum auctions, 5G bidding. Real estate tenders, Google AdWords, bidding for ad slots. 28. Zomato delivery zones, Voronoi regions. Concept, spatial partitioning. The scenario, there are 5 McDonald's outlets in a city. Which outlet should deliver to your house? The logic, you draw lines exactly halfway between every pair of outlets. This creates regions, polygons. If your house falls inside the region of outlet A, then outlet A is mathematically the closest to you. Real business use, 5G tower coverage, emergency response zones, which ambulance goes to the accident. School districts. 29. Simulating a bank lobby, simulation. Concept, Monte Carlo simulation. The scenario, a bank wants to change its layout. Instead of separate queues for each teller, they want one snake line, common queue. Will this work? They can't just build it and see. Too risky. The solution. They build a computer model, generate 1,000 random virtual customers, simulate how fast they move in separate lines versus one snake line. Result, snake lines feel fairer, first come, first serve, and are usually faster on average. Real business use, airport security checks, theme park designs, financial risk analysis, simulating a market crash. 30. Disaster relief in Odisha, humanitarian logistics. Concept: multi-objective optimization. The scenario: a cyclone is approaching Odisha. The government has limited helicopters, food packets, and medicine. Objective 1. Minimize loss of life, priority. Objective 2. Minimize cost. Objective 3. Maximize fairness. Reach remote villages too, not just cities. The conflict: reaching a remote village takes 5 hours, saves 10 people. In those 5 hours, the helicopter could save 100 people in the city. What do? The logic. OR uses weighted goals. $Z equals W1, text lives, plus W2, text cost, plus W3, text fairness, $. You assign a huge weight, $W1, to lives. The model creates a route plan that prioritizes saving the most vulnerable first. Real business use, NDRF, National Disaster Response Force, operations, vaccine cold chains, food distribution in famine zones. Conclusion: how to apply this tomorrow. You don't need a supercomputer to use operations research. You just need the mindset. The 3-step OR checklist for daily life. 1. Identify the goal. What exactly do I want? Maximize savings. Minimize time. 2. Identify the constraints. What is stopping me? Money, time, energy. 3. Optimize. Don't just pick the first option. List 3 options and check which one fits the goal best within constraints. Whether you are a student planning your study schedule, a shopkeeper stocking rice, or a CEO planning a merger, you are doing operations research. The math just helps you do it better.